Hey everyone, welcome to the channel. In this video we are diving into Wi-Fi security protocols, and this isn't just about, setting up a strong password. It's about understanding the whole range from a simple shared keys all the way to enterprise-grade certificate authentication. This will be a two-part series. In part 1, we'll explore Wi-Fi security protocols and authentication methods, breaking down how they actually work and how to configure them on Linux using tools like WPA Supplicant and Systemd Networkd. We'll unpack WPA2, then WPA3, and then move into the enterprise stuff, EAP-PEAP and TLS, and really highlight the specific weaknesses each new standard was built to fix. In part 2, we'll take it hands-on, setting up a proof-of-concept Wi-Fi network featuring mutual certificate authentication and automatic certificate rotation powered by HashiCorp Vault. I hope you find this interesting and learn something new along the way. My name is Philip. Let's get started. In a wired network, signal stays inside physical cables. If someone wants access, they literally have to plug into the network. But with Wi-Fi, your data is literally flying through the air. Anyone nearby with, let's say, the right gear can potentially grab it. That's the fundamental vulnerability of wireless networking. So, strong encryption, integrity checks, and solid authentication, these aren't just optional extras. They're absolutely necessary to stop eavesdropping or worse, message tampering. On Linux, Wi-Fi authentication and key management are handled by a tool called WPA Supplicant. It talks directly to the kernel Wi-Fi interface and manages association, 802.1x handshakes, the four-way handshake, all the good stuff. In short, it gives you layer 2 access to the Wi-Fi network. When you use something like Network Manager, it's actually WPA Supplicant running quietly in the background, doing the heavy lifting, associating your Wi-Fi interface with the access point, authenticating and negotiating encryption keys. Let's take a look at how that works. For this demo, I'll be using an Ubuntu 2404 long-term support machine as the client. It's equipped with a Wi-Fi card based on the Qualcomm Fast Connect 7000 chipset. In my experience, this chipset is one of the most reliable and fully functional Wi-Fi 7 options available for Linux right now. As the access point, I'll be using a Ubiquiti UniFi U7 Pro managed by a UniFi UCG Ultra controller. We'll be configuring the wireless connection manually using WPA Supplicant and Systemd Networkd instead of higher level tools like Network Manager or NetPlan. First, let's disable Network Manager so it doesn't interfere with our setup. Next, I will enable Systemd Networkd, which we'll use to handle IP layer networking, things like addresses, routes, and DHCP. Remember, WPA Supplicant only takes us up to layer 2. I will also remove the existing NetPlan configuration. NetPlan is basically a configuration abstraction layer. It just takes YAML files and translates them into backend configs. Alright, that should set up us nicely on the client side. We are also using pretty modern equipment here, which means we can take full advantage of the latest Wi-Fi security standards. Let's move on and connect the device to our wireless network. The first step is to enable Wi-Fi on the system. Let's begin by checking the current state of all wireless devices. This command shows whether Wi-Fi is blocked either by hardware, for example a physical switch, or by software. If it's blocked, we can unblock it using the unblock command. There we go. Wi-Fi is now unblocked. Next, we need to identify the name of our wireless interface. To do that, we'll list all available wireless interfaces using the IW command. The IW utility communicates directly with the Linux kernel's NL802.11 interface, allowing us to configure and query wireless devices such as listing interfaces, scanning for networks, setting channels, and adjusting parameters. Think of IW as the wireless counterpart of the IP command. Okay, our Wi-Fi interface is WLP6S0. We can verify its current status with the link command. At this point, we are not connected to any network. To establish a connection, we'll use WPA Supplicant, a service that manages Wi-Fi authentication and controls the association and connection process with the access point. First, I will navigate to its configuration directory and create a new configuration file. Note that the file name must include the interface name after the dash. In this file, we'll define our Wi-Fi networks later. For now, let's specify the control socket that we can manage the WPA Supplicant process from the command line. We'll also allow command line tools to update this configuration file. Next, let's start the WPA Supplicant service for this specific interface. We'll use the @ symbol followed by the interface name. To ensure the service starts automatically on boot, I will enable it. Now, our WPA Supplicant service is active and ready. The next step is to configure it to connect to a network. For that purpose, we'll use WPA CLI, a command line tool that talks directly to WPA Supplicant in real time through its control socket. Every access point periodically transmits beacon frames on its channel, usually every 100 milliseconds. These beacons announce the network name, supported rates, capabilities, security information, and channel, basically everything nearby devices need to discover it. The first step to connect is to scan for networks. This command cycles through all channels, listening for beacons. Each channel corresponds to a specific frequency within the Wi-Fi spectrum. For example, in the 5 GHz band, channel 36 sits at 5180 MHz. After scanning, we can list the results. Each entry shows the BSSID, that is the MAC address of the access point, meaning that one access point can advertise multiple networks. Then there's the frequency in megahertz the network is using. There are 3 Wi-Fi frequency bands commonly used today: 2.4 GHz, 5 GHz, and most recent 6 GHz band. Each offers different trade-offs. 2.4 GHz provides longer range and better wall penetration, but lower speeds. 5 GHz deliver faster throughput with reduced range, and 6 GHz, introduced with Wi-Fi 6E and Wi-Fi 7, offers even higher capacity, wider channels, and less interference due to its cleaner spectrum. You'll notice some networks are on 2.4 GHz, some on 5 GHz, and others on 6 GHz. Then there's the received signal level in decibel milliwatt. -30 is excellent, -60 is good, -80 is weak. Then we have capabilities and security features of the network, and lastly the SSID, that's the network name. Okay, let's try connecting to our first test network named Test WPA2. It uses WPA2 PSK key management. Key management is responsible for generating, exchanging, and refreshing the encryption keys that protects Wi-Fi traffic between the client and the access point. Then we see the network is using CCMP security protocol. Security protocol defines how the data is packaged, encrypted, and checked for integrity. CCMP is based on a 120-bit AES block cipher. I will start by executing the add network command. It will return a network ID that we'll use in further commands. First, let's set the SSID, the network name we are trying to connect to. Mind that I'm referencing number 0, that's the internal index for the network block inside WPA Supplicant. To authenticate to the network and to prove that we are authorized to connect, we'll use the most basic method called the pre-shared key. That's a single fixed password for the entire network. The pre-shared key is usually stored on the access point or on the controller if you have a managed network. Then let's specify the key management method. Key management defines how encryption keys are negotiated. Our network uses WPA2 PSK. PSK stands for pre-shared key. This is probably what most home users still have. Key management defines how the clients and access point agree and install encryption keys. pre-shared key is the most basic method. We just prove our identity by knowing the passphrase. So everyone uses the same password, the pre-shared key. How does that stop me on the same network from sniffing my neighbor's traffic if we are both connected? That's where key derivation comes in. It's a neat trick. The shared password, the pre-shared key, isn't used directly for encryption. It's used as an input to generate something called a pairwise master key, or PMK. Then this PMK is used in what's called a four-way handshake between your device and the access point. And the result of that handshake is a unique session key, the pairwise transient key, or PTK. It's unique for every single client. So even though you all started with the same password, you each end up with your own secret key for encrypting your traffic. That generally prevents one client from decrypting another's data. Next, we define a security protocol used to encrypt traffic between client and the access point. We'll go with CCMP. It's based on 128-bit AES block cipher. If you see older things like TKEAP or, heaven forbid, WEP, those are just insecure relics. You absolutely should not be using them. CCMP is the minimum you should accept today. Next, let's set the security protocol for encryption of broadcast and multicast traffic. We'll use CCMP as well. Next, let's disable mesh forwarding for this network. Now let's enable this network so WPA Supplicant can try to connect to it and select that network. It tells WPA Supplicant to immediately connect to the network. Okay, we are connected. By running the status command, we can see more details. Let's now save the configuration. If we check the WPA Supplicant config file, we'll see the network block added. As we set up our WPA Supplicant service to be enabled at boot, it will automatically connect to the network every time the service starts. Let's quickly look at how the network was configured on the access point. Here's the network name, the SSID, the pre-shared key. Here's the Wi-Fi band we are using, 5 GHz. BSS transition management is a mechanism that helps clients switch to a better access point more intelligently. In short, the access point suggests to the client that it should move to a different access point with a better signal. The client decides whether to accept the suggestion. Basically, the access point sends a BSS transition management request, which includes a list of nearby access points and their parameters. You should keep it enabled as most devices support it. Then the security protocol is set to WPA2 and management frames protection is disabled. Going back to our client. We did run the commands in interactive mode, but usually you just prefill the configuration file yourself. If we look at our network interface, we'll see it's up, but it doesn't have an IPv4 address. That's expected, as WPA Supplicant only handles layer 2. We'll let systemd network D handle DHCP. First, let's go to the network configuration folder. I will create a new configuration file. We'll select the Wi-Fi interface and then enable the DHCP client. I will also set the route metrics to 2048. The higher route metric ensures the wired connection is preferred when both are active. Let's save the configuration file and restart systemd network D. Our interface got an IPv4 address assigned from DHCP. If we look at the routes, we see that the default route we got from the Wi-Fi interface has a higher metric than the default route we got for wired connection. The default route via Wi-Fi connection will be less preferred than the default route via wired connection. Basically, Wi-Fi connection won't be selected unless the wired connection goes down. Finally, we can check the link quality and connection stats with the IW link command. We are operating on 5200 MHz using an 80 MHz channel with Wi-Fi 7, which gives us a negotiated link speed of about 1.4 gigabits in ideal conditions. And that's it. We've successfully connected to a WPA2PSK network using only command line tools. WPA2PSK with CCMP is the minimum level of Wi-Fi security you should be using today. It provides strong encryption and per-device session keys that protects your data from eavesdropping. However, WPA2 does have one notable weakness. Because everyone uses the same shared password, the pre-shared key, attacker can just sit nearby, capture that four-way handshake happening over the air. They don't even need to be connected. They capture the handshake, take it away, and then use computers to just guess the password over and over again. They compare the results against the captured handshake data until they find a match. It's an offline dictionary or brute force attack. And importantly, they don't need to interact with your live network at all while they are guessing, which makes it slow, maybe, depending on the password strength, but undetectable. They could crack it weeks later. That's why modern networks are moving to WPA3, which replaces WPA2 PSK with a stronger authentication method called SAE, Simultaneous Authentication of Equals. Its key benefit, it kills that offline dictionary attack vector. With SAE, every single password guess must interact with the live access point. The attacker can't just capture a packet and guess offline anymore. They have to talk to access point for each attempt. And because they have to interact live, the access point can actually see this happening. It could potentially notice repeated failed attempts and throttle them, slow the attacker down. It makes brute forcing dramatically harder and much slower. So this WPA3 SAE method still uses a pre-shared key, but is resistant to offline dictionary attacks. Alright, let's drop the current connection and scan again. If we look at the scan results, we'll find a WPA3 network named test WPA3 with the SAE key management. There's one more feature enabled, FT, that stands for fast transition, also called fast roaming. Without fast transition, when a device moves to a new access point, it has to do a full four-way handshake again, which can cause delays or brief connection drops. With fast transition, part of the key derivation happens ahead of time, so hands-offs are almost seamless. Mind that fast transition is not exclusive to WPA3. You can use it with WPA2. Let's connect to that network. For that, I will create a new configuration. We got a new ID of 1. Now let's set the network name we want to connect to. Then let's set the pre-shared key for that network. Next, let's set the key management method to SAE, that's WPA3. Then, let's set the security protocol for unicast traffic to CCMP. Let's also set the security protocol for broadcast and multicast traffic to CCMP. There's one more security improvement that comes with WPA3, management frames protection. It can be enabled for WPA2, but in WPA3 it's mandatory. Generally, Wi-Fi frames are grouped into three main types: data frames that carry the actual payload, control frames that control access to the medium like acknowledgements, request to send, clear to send, and so on, and management frames like beacons that announce the network, authentication and deauthentication frames, association or deassociation frames, and so on. Let's enable management frame protection. 0 is off, 1 is optional, and 2 is enabled. Without this protection, anyone could just spoof a deauth frame pretending to be the access point and kick legitimate users off the network. Simple denial of service. PMF adds cryptographic integrity protection to many of these crucial management frames. This makes spoofing those kick-off messages incredibly difficult, significantly boosting network stability and resilience. Finally, let's disable mesh forwarding for this network. Enable it and tell WPA Supplicant to immediately connect to it. If we look at the status, we'll see the connection has been established. Now let's save the configuration. If we look at our configuration file, we now see two profiles. The previous one is disabled and the current one is enabled. Just by changing the key management to SAE and enabling management frames protection, we've secured our network against offline dictionary and brute force attacks, as well as disassociation attacks. Though online guessing remains theoretically possible but highly impractical. SAE requires every password attempt to interact with the live network. Guessing password is still possible, but it's much slower. Each attempt must happen against the access point, allowing throttling and alerts for repeated failures. Also, with PMF enabled, attackers can no longer easily spoof disassociation and deauthentication frames to kick users off the network. Let's look at the link quality. This time we operate on 6 GHz, two spatial streams with 320 MHz channel width that gives us negotiated link speed of around 4 gigabits per second under ideal conditions. Let's quickly look at the access point. Here's the SSID, passphrase. Here we select the Wi-Fi band to 6 GHz, we enable BSS transition and fast roaming. The security protocol is set to WPA3 and PMF is enabled by default. So WPA3 is definitely a big step up. SAE stops offline cracking. PMF stops easy disconnect attacks, but both WPA2 PSK and WPA3 share a fundamental, almost administrative flaw, that is, zero accountability, as every single user and device possesses the exact same secret key. If that single password leaks, you have absolutely no idea who leaked it. Was it an employee, a guest, a compromised device? You have to change the password on every single device connected to the network. Your laptop, your phone, the smart thermostat, the printer, everything. Imagine doing that in an office with hundreds of devices. It's just not scalable. The administrative burden alone seems like reason enough for businesses to move beyond shared keys. Which brings us to the enterprise side, WPA EAP, using the 802.1x framework. This is where we shift from one secret for everyone to unique credentials for each user or device. 802.1x changes the game entirely. Authentication isn't handled by the access point itself anymore. Instead, the access point acts like a simple gate and it passes the authentication request off to a dedicated server, usually a Radius server. That Radius server is the one that actually checks the credentials. It might check against a local database or by connecting to a directory service like LDAP, Microsoft Active Directory, or other identity provider like Okta. And crucially, the access point blocks all normal network traffic from the client until the Radius server says, okay, this user is legitimate, and the huge win here is accountability and manageability. The network admin knows exactly who is connected. If one person's credential gets compromised or they leave the company, you just revoke their access on the Radius server. Everyone else stays connected. No mass password change chaos. The 802.1x framework separates roles into three parts. The supplicant, that's the client device, the authenticator, that's the access point or switch, and the authentication server, that's the Radius. The authenticator just relays EAP messages. It never sees the actual credentials. So let's look at the first common enterprise method, EAP-PEAP. It usually involves usernames and passwords. But we know sending passwords unprotected is bad. How does PEAP protect them? It uses a two-phase approach. Think of phase 1 as building a secure tunnel. The client connects to the Radius server and they establish an encrypted TLS tunnel between them. To set up this tunnel, the Radius server presents its certificate to the client. And this is critical. The client must validate the server certificate using a trusted certificate authority. Then comes part 2. Inside that secure tunnel, the client sends its actual credentials. Usually, this is done using a protocol like MSCHAP v2, which involves the username and hashed version of the password. Because it's inside that already encrypted TLS tunnel, it's protected from eavesdropping on the Wi-Fi network itself. Let's move to the demo. First, I will disconnect from the network, then let's initiate a scan. Here's our WPA3 enterprise network with PEAP authentication. This time, let's perform the setup via the configuration file. First, let's disable the previous configuration and add a new network block. I will set the SSID. Next, let's set the key management to WPA EAP as opposed to WPA PSK. The access point supports WPA2 SHA-256 variant. It still uses 8021X authentication, but replaces SHA-1 with SHA-256 in parts of the key derivation process, offering stronger cryptographic robustness. Next, let's set the inner authentication type to PEAP. That means MS-CHA protocol will be used to validate credentials within the tunnel. Unicast encryption stays the same, CCMP. Broadcast and multicast encryption also stays the same, CCMP. Now let's provide the credentials. The username, then the password. Those are the credentials we've set on the Radius server. Next, let's set the inner authentication to MS-CHA v2. We'll also enable management frames protection. And finally, a very important step. We need to provide the CA certificate so that our client can validate the certificate presented by the Radius server. Let's save the configuration. Our Unify USG Ultra is running Radius server, so let me log into the Unify controller and download the CA certificate. Before enabling the connection, let me quickly validate the Radius server certificate against the CA certificate manually. To retrieve the Radius server certificate from the Unify controller, we'll use the EAP-TLS tool that can perform a complete EAP authentication exchange against the Radius server and export the received server certificate for manual inspection and validation. Here's our config for the EAP-TLS tool. Let's run the tool pointing to the Radius server, extracting the server certificate to a PEM file. Okay, now let's verify the server certificate that we got from Radius using the CA certificate from Unify. All looks good. Let's go to our WPA CLI and issue the reconfigure command. That will reload the configuration from our configuration file. Then let's list our configured networks. New configuration is there. Next, let's select the network that will tell WPA Supplicant to immediately connect to it. If we look at the logs, we see that EAP authentication started. PAP method was selected, Radius server presented its certificate, and that certificate verification was successful. We can issue status command to get more information. Okay, all looks good. Let's look at the wireless controller. Here's our built-in Radius server listening on port 1812 UDP. Here's the shared secret that is used between the access point and the Radius server for secure communication. Here are the local user credentials, username and password. Now if we move to the Wi-Fi configuration, here's the network name, the SSID. As you see, there's no shared password among users anymore, as each user has unique credentials. The security protocol is set to WPA3 Enterprise. The Radius profile points to the default built-in Radius server. EAP-PEAP is a big step up from a pre-shared key, but it still has its weaknesses, most notably the evil twin attack. This attack exploits potential misconfiguration or, frankly, user carelessness on the client side. How does that work? Remember phase 1, where the client must validate the Radius server certificate? Well, what if the client is configured not to validate it properly, or the user just clicks connect or trust on a warning? An attacker can set up a fake access point with the same network name, the evil twin. When your device tries to connect, the attacker fake Radius server presents any certificate. If your client doesn't check it rigorously against the proper CA certificate, the client thinks it's built a secure tunnel, but it's actually built with the attacker. The client then happily sends its MS-CHA v2 challenge response, essentially its username and password hash, straight through the attacker's fake tunnel. It's a classic man in the middle. The attacker intercepts the credentials, potentially relays them to the real network, so the user doesn't notice immediately, but the damage is done. On top of that, PEAP still relies on passwords that can be phished, guessed or stolen. Users have to remember them, change them, reuse them, all the usual password problems. This leads us to EAP-TLS, considered to be the most secure authentication protocol for Wi-Fi network. With EAP-TLS, the client must also provide its identity to the server using its own unique client certificate and corresponding private key. So both sides have to show their credentials cryptographically. passwords are completely eliminated from the authentication process. This kills the phishing risk associated with the passwords. It also fundamentally prevents the evil twin attack we just discussed, because even if an attacker sets up a fake access point, they cannot possibly have the legitimate client's unique private key needed to complete the authentication, as the private keys never leave the client device. Plus, certificates have a built-in expiry date. So even if a device containing a client certificate and key is compromised, that credential is only valid for a limited time. Unlike password, it limits the window of opportunity for an attacker. Let's move to the demo. I will first disconnect from the network, then let's initiate a scan. Here's our demo network. We are not only changing authentication from PEAP to TLS, but also changing the cryptographic strength, cipher suits, and key management requirements. We'll use the so-called Suite B 192 security level. It's not required for EAP-TLS to work. We could use EAP-TLS with our previous configuration, but we'll go for maximum security. That means HMAC SHA 384 for key derivation, ECDH ECDSA with P384 curve for key exchange, and AS256 GCMP for data encryption and integrity. It provides roughly 192-bit equivalent security strength. Let's now open our configuration file. I will disable the previous network configuration. Now let's add a new configuration block. First, I will set the SSID of the network we want to connect to. Then, let's set up the key management to WPA EAP Suite B 192. Then let's set the EAP method to TLS. So both the client and the server must provide their identity using certificates. Then let's set the unicast encryption suite to GCMP and multicast broadcast encryption suite to GCMP as well. Let's also enable protected management frames. I will set the identity to anonymous, so our real username isn't exposed before encryption. Now the most important piece. We need to provide the CA certificate to validate the certificate provided by the Radius server, but also we need to provide our certificate that will present to the server for authentication. We'll also need a key to confirm the ownership of the certificate. Okay, all is set. Let's save the configuration. Now let me go to WPA CLI and reload the configuration with the reconfigure command. If I list the networks, we'll see our new config. Let's tell WPA Supplicant to connect to that network. If we look at the logs, we'll see the EAP authentication started, TLS method was selected, that's mutual certificate authentication. Then we see the client successfully verified the remote server certificate. Client also presented its certificate to the server that validated and accepted the certificate, hence the final result is success. Let's look at the status. Everything looks good. If we look at our Wi-Fi controller, we are no longer using built-in radius, but delegate the authentication to external free radius server. If we look at the Wi-Fi configuration, it's almost identical to the previous one. The only difference is the radius profile and high security mode. How does the radius server handle TLS authentication and certificate renewal? Just to give you a sneak peek. Here's our client certificate. It's valid for just 10 minutes. However, there's a service running called the HashiCorp Vault Agent that automatically refreshes the certificates behind the scenes. Mind that 10-minute certs are fine for demo, but typically enterprise setups use hours or days. In the next video, we'll set up a certificate authority using HashiCorp Vault server, then configure HashiCorp Vault agent to automatically renew the certificates and set up free radius for EAP-TLS authentication. Thanks for sticking with me through that detailed look at Wi-Fi security protocols on Linux. We've seen how security has evolved and why moving beyond a simple pre-shared key is so important for scalability and accountability. What security protocols are you running on your own network? Let me know down in the comments. In the next video, we are building the real deal, a full EAP-TLS setup with a HashiCorp Vault CA and free radius. As always, thanks for watching and I'll see you in the next video.